So, this I would probably write down. And let's see. Zoom in a little bit. There. So, that standard form of a circle, you've got it. You can have it there on your screen too. It's on the next slide. Is x minus h squared plus y minus k squared equals r squared. And in this equation, the center is at hk and the radius is r. So for these, for circles, you can really think about this just like transformations that we've done, but there is a little bit of a difference because both our x value and our y value are on the inside of the parentheses here. So remember that whenever we were talking about shifting things left, right, up, down, we were really only dealing with functions where it was like f of x equals. And if something was on the inside of the parentheses, that moved left or right. And if something was on the outside of the parentheses, that moved up or down. Here, if you have something inside of the parentheses with the y, that's going to move the circle up or down, but in the opposite direction because it is in the parentheses. Over here, just like it was with the functions, we got something inside of the parentheses with the x is going to move left or right in this case. So I'm going to anonymize you so that you're no longer yourself. So when I go look at this here, I've got everybody's name is hidden. So on the next slide, there it asks for you to give the equation of that circle. And then on the one after that, it's going to ask you to graph a particular circle. So play around with those for a minute and see. Our answers. And most everyone has a x minus 2 squared, y minus 1 squared. Okay, I do see a 3 right here. I think that Grace may have just counted wrong on that. I do see this one up here where it looks like this person was probably like trying to replace the x's and y's as well. The x's and y's you want to leave in your equation, right? So you want to have your x's and your y's still there, but the h and the k get replaced. So the x minus 2 squared and the y minus 1 squared, that gets your center in the right place. And then I think a few of you changed it when I started putting stuff up here because there were more, but like you can see right here, this top one had an 8 squared. They're changing it right now to a 4 squared. But what did they do wrong if they looked at 8? That's the diameter. That's all the way across the circle, so you want to cut that in half. Somebody, oh, right here, this person has 16 instead of 4 squared. Is that okay? That's fine. 4 squared is 16. That's wonderful. Guadalupe here at the bottom just needs to replace that R with a number. So with the radius, it needs to be plugged in there. So you can put the 4 squared or you can just put the 16. Really either is fine to get that equation. So use that to help you on the next slide if you haven't already gotten that one. We are looking for a center at, what did it say? I've forgotten. At 2, -4. So 2, -4 should be in that fourth quadrant. The center should anyway. And then the circle has to pass through 2, -1. So I am interested in a couple of these that don't look like circles to me. So William Shakespeare. When did they start putting... Why is he here? It's always mathematicians. So, okay, I think this one is actually okay, probably. The point 2, -1 is right here. And the equation looks good. You got -2 + 4. But it doesn't look right, does it? It looks like an ellipse. I think that somehow you have just... I think that William Shakespeare here has just, like, messed with your, like, zoom here. If you hit the house button didn't do anything.
That's the basic trying to figure out.
Oh,
This is me. I pressed the house button.
you hit the house. Let's go, if you click here and click zoom square, I guess it was already in zoom square before, but if you hit the house button, it went back to a different thing. So, this one is completely right. It was just that zoom, hitting that house button made that zoom funny there. Because I think the house button makes it 10 by 10 on both axes, but where we're looking at this is wider than it is tall. It makes that look funny. But if you hit that wrench and hit zoom square, then I think this looks beautiful. And then, let's see. I think most of the rest of these are looking the same. I do want to show you something kind of cool here that I did not know about. For this, if you are trying to make sure your center is in the right place here, or just want more specific points, I did not know that you could do this, but if you put points in and you hold, click right here, and you click right here until it's put lines, it will connect the points that you have put in. And I did not know that it would do that, because I don't think I've ever tried to put in a list of points like that, but apparently it will do that. That could potentially be useful in your project that you're going to be working on there. So I thought that was interesting. Okay, so we're doing fine there. All right, on to our next. Let's see. Okay, so our next part is parabolas. So parabolas should be something that you're very familiar with, particularly whenever it's a y equals parabola. Okay, so your vertex form of a parabola, whenever you have y equals, is a times x minus b squared plus c. It's basically like the transformation version of it, right? This a right here stretches it out or squishes it down. The b shifts it to the left or the right in the opposite direction. The c moves the parabola up or down. And so your vertex would be BC here, and this parabola is either going to open upwards or downwards. So these types of parabolas we've seen a lot before. We've dealt with them. But there is a second type that I don't think you have worked with in any other class. And that is going to be the inverse of this parabola. Now, will the inverse of this parabola be a function? That's a good review from did it have an inverse question? Did it ask for inverse or did it ask for like quadratic? I'm not supposed to ask. I can't know. It did inverse. Okay. I was kind of hoping for that one. I think we probably got that. So like this one does not have an inverse function, right? Because each input value does not have a unique output value right here. But it can still have an inverse. That inverse is just not a function, right? So the inverse of this is if you switch the x and y's. Okay, so this is one that I don't believe, have seen. And that is a parabola whenever we have x equals. It's going to be a sideways parabola. And so the formula for this is going to be x equals a times y minus b squared plus c. Looks like the one you just wrote down, except for you switch your x and y's. You have to be careful with this one for the vertex. All the transformations are backwards because it is an x and an x equals equation. So like this c right here is actually moving the graph left or right, and it goes in the correct direction. So that's your x coordinate. The b right here is inside of the parentheses, so it's opposite direction, and it's in there with a y, so it's your y coordinate for that. And these parabolas are either going to open to the right or the left. Okay, so once you get done copying that down, your next two slides are going to ask you to graph specific types of parabolas. So go try those problems. For this, I see lots of you that have graphed the points. It looks like it's working out. Let's just click on one. Mary here, we got the point 3, -4, and we've also got the point 1, 4 graphed. We got the equation y equals 2 times x minus 3 squared minus 4. So that vertex, use the opposite sign for the x because it's on the inside of the parentheses, right? You need to go to the right 3, so you put a minus 3 here. You need to go down 4, so you put the minus 4 here. That gets your vertex in the right spot. And then you can kind of just play with that number out front until you get it to go through that point that you're looking for. There are algebraic ways to do it, but we won't get into those. Most of what we're going to be doing is knowing the general shape and playing with it to get it to work, which is still actually very important mathematically. So questions on that one? Looks like most of you got that one there. Those look pretty good. Let's see what we got over here. We've got a few that are still opening to the right. We got a few that look different, but I think it's probably going to be our scale. Let's look right here. So for this one, we've got, we wanted the point -3, 2. So this one goes to the right point. Notice the -3 goes out here on the end, right? Because that's actually your x. That's what's happening to the x. You want the x to go to the left 3, and it goes out here. The y, use opposite sign. It goes on the inside, right? So did some of you have to like switch those numbers because you were thinking of it more like the last problem? And then to get this to open to the left, what did you have to do to the equation? We had to use a negative number over here for the a, right? In fact, this was a good one for me to click on here because Gloria used a slider right here. So notice if I go back over here to where my slider is positive, I get a parabola that opens to the right. But when I flip it over here to negative, I get one that opens to the left. And this one did not specify another point that it had to go to. It just had to open left. So you could really use any number over here for your A as long as that number is negative. All right, good for those. All right, so we've got circles, we got parabolas. Those are our two most familiar ones, the ones that you have seen before in classes, although we had not seen the sideways parabolas. So some of my favorite ones are ellipses. So this is your equation for an ellipse, which is just really an oval. So I would copy that down. And it really works a lot like a circle. In fact, you can, if your A and your B are the same number, you'll get a circle here. So the center part works just like a circle. You got x minus h squared and y minus k squared. For ellipses, the distance from the center to the left and right vertex, that's going to go underneath your x, and it's going to be squared. So like for here, I've got my A value would be 3 right here. So I would have x plus 1 squared over 3 squared for the x part of this problem. In fact, I can't write on that, but I'm going to write on it. So like for this picture, your center is at -1 and +3. Your A value is 3. Your B value is 5, I think. 1, 2, 3, 4, 5. Yes. Right. So you would have x plus 1 squared over 3 squared plus y minus 3 squared over 5 squared will equal 1. For ellipses in standard form, they're always going to equal 1. And if you want to adjust the size, you change these numbers underneath your x minus h squared and your y minus k squared for those. If you want the ellipse to be wide instead of tall, you would have your A value is going to be bigger than your B value there. So try the next couple slides on your own. Okay. So if we look through here, I am seeing that most of these have an x plus 4, y minus 1. I do see an x minus 4, y minus 1 here. We want to use opposite signs for both points here, and your center is at -4, right? Yeah, -4, +1. So you want to use opposite signs for both, at -4, +1. And then your distance from the center to the right vertex is 2. Underneath the y, you should have the 4. And you should have squares with both of those. This one right here has a 5, where it should be a 4. This person put x minus -4. Is that okay? That one's all right. The same as x plus 4, right? So that's okay. Ooh, here's a good question. Is this okay? -2 squared and -4 squared. Let's see. I'm gonna type this into Desmos. In fact, one of the best things about Amplify is I think it lets us copy and paste. Here, so why is it not got anything? We got nothing. But it's not giving me an alert. something should be graphing. Now, if I put a parentheses around this -2, I think something's going to show up. There it is. But without those parentheses, ooh, look what happened there. That's kind of crazy, right? And here, it's not graphing anything for us. I think it's imaginary, maybe. Because if you put a square with a -2 and there are no parentheses, it is technically only squaring the 2. So you have like a -4 here on the bottom and a -16. And those values can't be negative. If you put them in parentheses, you can. I would just not use negatives for this. I would just use positives every time. There. Okay, let's look at the next one here. All right, we're supposed to graph an ellipse that passes through 0, 6, and -5, 2. So, let's look. We have some options here that look different. But I see that a lot of people have graphed the points, and it looks like they're okay. So let's just look here. This person has this person used sliders for everything, right? So their H is 1, their K is 2, their A is 6, their B is 4. There. And it looks like, excuse me, does look like that. I don't know. If we zoom in, it may not. Actually, I think this one's a little off. If you zoom in a lot, that one's off just a little bit. A little bit. There. Let's go to this one because it looks like theirs is kind of the same. This one has a center at 0, 2, and a 5 squared and a 4 squared, and I think that one does go through the points exactly. There, so I think this one works right here. So this is an option, but that doesn't necessarily mean that you need to change what you had. Because some of you just thought about going through those 2 points differently, right? For example, let's see about this one. This one, I think we might be off a little bit here. I think that one's going to be off if we zoom in. Yeah, it's off a little bit. But if we fiddled with it more, could you get this one to work? You could. It could go through those 2 points that way. Let's see. Oh, wow. Let's see. This person didn't think of these 2 points as the top right part of the ellipse, but instead the top left. Instead the bottom right. And I think this one works fine. This has a center at -5, 6, and you got a 5 squared and a 4 squared here. That one works, right? So you can have different options for some types of problems like this that can still make both of those true for that. All right, we've got one more to look at, and then we are going to look at what we'll do for our project. So this is a hyperbola. Now, look at this original, like this top one right here. What is the only difference that you see between the top, or that first equation, and an ellipse? That middle is a minus sign, right? So the equations are almost identical, but the graphs look very, very different. You can see here, this is a hyperbola, and that hyperbola looks very different than the ellipse. You also can switch these terms here where your y term is positive and your x term is negative. that's going to cause the parabola to open up and down instead of left and right. So I'm going to let you write these things down so that you have them, and then your last two slides have some parabolas for you to play with. There. So we are looking for parabolas that open up and down and have a center at 3, -5. So there are several of us that are still stuck with a left and right, but we've got many here that have up and down. So for the center 3, -5, you do just like a circle. You're going to have x minus 3, and you're going to have y plus 5. And notice here that if you put the y first, so the y term is positive, and the x term is second, it is negative, that you're going to get a parabola that, not parabola, hyperbola that opens up and down. All right, so you want that y to be positive, you want it to open up or down. Notice this person used sliders, so this is a good one to click on right here. You can adjust these numbers, and it changes what that hyperbola looks like. You can see A doesn't really change anything about the center, or nothing changes about the center either way. Center's in the same spot right there. We got 3, -5. It stays there. But this sort of makes it wider or shorter. This sort of moves it up and down, and also adjusts the width a little bit there too. So, main takeaway I want you to have here though is that the y part needs to come first if you're opening up or down, which means over here to open left or right, we are going to use the x is going to be positive, the y will be the negative. We got x minus 0 and y minus 4. Does Grace have to put the 0 right there? Don't have to. So sometimes, like, if you were to see this somewhere else, it may not have it, but it's fine for it to be there. And then you've got various A's and B's that you can play with there, but it doesn't change the center. So those are our 4 types of conic sections. We have circles, we have parabolas, we have ellipses, and we have hyperbolas. I think that it is interesting that their formulas can look very similar in a lot of ways, particularly between the circles, ellipses, and hyperbolas. But their graphs look very, very different. Ellipses and hyperbolas are the most drastic example of that, where you go from an oval to this funny shape right here. So I'm going to show you guys what you're going to do for your project. And I was looking for examples, and for some reason I can't find them. And I'm going to have to look for specific students. So let's see. We need Desmos Art Project. I'm going to open this, and I've printed this one out for you too. Going to take what you've learned in class, and you are going to make a picture in Desmos. You are required to use at least one of each of these 5 right here, which come from units 1 through 3. So a polynomial of 3rd degree or higher, you have to use a rational, you have to use a log, you have to use an exponential, and some type of sinusoidal. It can be cosine instead of sine if you would rather. There. So you have to have all 5 of those, at least one. You can use more than one if you want, because sometimes you need more than one to get the picture to look like you want. You must also use at least one each of these 4 types of conic sections that we just went over. So those all must be there. You can include bonus elements. So bonus elements are going to include polar equations. You can use polar equations. You can use other trig functions besides sine and cosine, so tangent, cotangent, secant, cosecant. Or I just put other advanced functions. So if it is more complicated than that. You also may want to use things like lines or points. You definitely may want to use those to get your picture to look the way that you want it to look. They're not required. They're also not extra credit because they should be very basic for that. If you are unsure about whether something counts as an advanced function or not, just ask me and I'll let you know. You get a maximum of 5 bonus points for those bonus elements. So you can include more if you just want to do it to make your picture look good, but I'm capping you at 5 so that you can't make a 127 on this assignment here. So you'll be capped at 5. The other reason that I love this project is it is also very, very easy for me as well. Because when I grade this, I'm just going to go through and check off to make sure you have all 9 of these. That is going to be 90 points. 10 points apiece. You got to have 1 of each, right? So I will check off to make sure you have at least 1 of each of these. I'm designing this because I want it to be a good grade for you. I could get way more intense on how I graded it, but I want it to be a good grade for you. You will get 10 points worth of creativity here. And that totals up to 100. You have a possibility for bonus elements. And then at the end, I'm going to send out our pictures and let each class vote on the best, and that person can get another 3 points there. I guess we could do like a 3, 2, 1, first, second, third place there. It has to be a picture. So I have to know that you are trying to make a picture of something. It cannot be 9 random polynomials, rationals, logarithmic, exponential sign. It can't be totally random. If it is random, I'm going to give it back to you until you do it over again. It doesn't have to be great, but I have to see that you're trying to make something here, right? And I'll try to find a few bad examples too, but like you can have a pretty bad picture and it's going to get a 90, right? Yes.
Could a polar equation count as a sinusoidal equation if we sign the polar equation?
No, they'll be separate. They'll be separate. This can look a lot of different ways. Let me give you a few tips. Now, if you are interested on here, there is a link right here that has a lot of YouTube videos on Desmos Art tutorials. So if you click on it, it's just got the paper that I gave you, the rubric, and a Desmos Art tutorial video. You don't have to look at those. That's just if you want to. I am having trouble coming up with, the only one that I've got really wasn't from Precal, and it is crazy good, but I'll look for a few more here in a minute and I'll show you. But a few things that you need to know, like let's say I want to do x squared plus y squared equals 6 squared. But maybe I don't want that whole graph, right? Maybe I want to like cut it off. Maybe I want a sunset, right? And I want to cut it off. In fact, maybe I want a mountain. Y equals negative x plus 2 squared plus 6. No. I'm going to move it over. 3. Put a 0.5 out here. There's my mountain. I want another one on the other side. Like that. There. Oh. Let's make my radius smaller. And let's move that circle up. Let's go back down on the radius. Let's go a little higher. You can see you're just kind of playing around. Like, maybe I just want that circle to show up here, right? I only want it to go from here to here. Notice your y coordinate is the same in both places. You got 5.1089849. So if I go over here to that circle and I do squiggly brackets and I do y is greater than that number, now I've only got the part of it that I wanted. You can even do crazy stuff like make it less than. You would have to get it go all the way down, you'd have to do something different. Like you can shade it by using less than or greater than signs or less than or equal to signs instead of those. If you want different colors, do I remember how to do that without having to there's a way. I don't remember the way. Oh, I do remember something. I'll show you in a minute how to get different colors if you want different colors. I'll have to go look that one up too. I can't remember how to do it. Or you can just use standard colors if you want. You know, here, if I want to cut these mountains off right here, I want my blue mountain to stop right there at 0. I can do squiggly. Actually, I really want it to stop right here too. So I could do squiggly bracket, negative 6.4, negative 6.4, whatever, less than x, less than 0. Cut that mountain off. Then I could go over here. I could do 0, less than x, less than 6.45, whatever. There. So my picture's already starting to come together, right? For that. And I've got 2 of my conic sections already. So that's the idea that you're going for. If you want to see some over-the-top ones, this was not calculus. So this was several years ago. This one is Connor Balls. So Braden's brother. This was his. He had a race car that he animated here. So that one is driving down the road. So you can see the lines going by as it drives down the road. So you can go over and beyond if you want. There's a good chance you'll win the contest at the end if you do that. But of course this would be extra good there.